Okay, being recorded. Yeah, being recorded. Well, thanks, Bill, for accepting to come here. You can go ahead, give us your talk.
Okay, so thanks so much for giving me this opportunity from my painting studio here, away from my dogs. So I'd like to talk about the Cesaro operator. And this is some thoughts on a problem of Halmos. So this problem has been solved. These are just some thoughts I've been having about this. So it's going to be essentially about the square root of the Cesaro operator and various things connected to that. So the Cesaro operator, it's inspired by this matrix called the Cesaro matrix. So it's an example of what's called a terraced matrix. And the terraces are the reciprocals of the integers. Right, so first I'd like to just consider this as a matrix. So it's a lower triangular matrix. We're not talking about an operator yet or anything. And I want to look at this as a linear transformation on the set of all complex sequences. So for any sequence of complex numbers, I make that a column vector, and then left multiplication by the Cesaro matrix gives you these averages. So this is the average of the first term, the average of the first two, the average of the first three, and so on. Because the Cesaro matrix is lower triangular, I can multiply it by any vector and it makes sense, and I don't have to be concerned about any convergence issues or anything like that. All right, so now I want to let the sequences belong to a certain Banach space, and it'll actually be a Hilbert space. So I want to look at the square summable sequences, that's known as little L2. And a result of, it appears in a paper of Brown and Halmos from 1965, it says the Cesaro operator is bounded on little L2, and the norm is equal to 2. Since I'll be using a piece of this proof later on, let me give you an outline of some of the ingredients in it. So the boundedness of the Cesaro operator, it's a little technical, but it follows from either one of two things, Schur's theorem, which gives you a condition on when an infinite matrix defines a bounded operator on little L2. So if you're good at adding series, and I have taught Calc 2 enough times, I have to say I'm excellent at it. You can actually check that the conditions of Schur's theorem are satisfied, and the Cesaro operator will take L2 to itself. Or if you want to go old school, there's a result of Hardy called Hardy's inequality, which you can use to show the boundedness of C. Now let's talk about the norm. So if you take I minus C, that's a lower triangular matrix. If you take I minus C, the I is the identity operator, minus C star, that's an upper triangular matrix. Amazingly, when you multiply that all out, you actually get a diagonal matrix. And the norm of a diagonal matrix is something you can compute. So to get the norm of I minus C squared, you use the sort of the C star algebra identity for operators. And then the norm of the diagonal matrix is the sup of the entries, and you can see that the sup of the entries is equal to 1. So the norm of I minus C is equal to 1. So if you're taking notes, maybe jot that fact down. We'll use it later on in the talk. But now you can get at least the upper bound for the Cesaro operator. So the norm, you use a little bit of the triangle inequality. The norm of the identity is 1, and we just showed that the norm of I minus C is also 1. Okay, so that's the upper bound. The lower bound, it's a little bit of a technical detail, but you can find a sequence of unit vectors from L2, and you apply the Cesaro matrix to it, and you can get it approaching 2 from below. So that'll give you a lower bound. It's a technical detail that I choose not to get into here. Now, one of the things we're going to need to help us understand the Cesaro operator and mainly the Kriete-Trutt result, which I'm going to use, is I want to change perspective here. So I want to, you can equate L2 with the Hardy space. So anyway, I'm sure we all know this little detail. So if I take all formal power series and where the Taylor coefficients are from little L2, I'm going to call that the Hardy space. Now, right now, this is just a set of formal power series, but you can actually show that the radius of convergence, a little bit of the Cauchy-Schwarz inequality will show that the radius of convergence of this power series is, for any H2 function, is greater than or equal to 1. And so this is going to define an analytic function on the open unit disk. Okay, so now the Hardy space is actually a vector space of analytic functions. And now you can actually make it a Hilbert space. So I define the inner product on H2 being the kind of the L2 inner product of the Taylor coefficients of F and G. Now, for those of you who know more about this, using something called Fatou's theorem, which gives you the existence of the radial limits almost everywhere on the circle, and then you use the classical Parsifal's theorem, you can actually rewrite this sum as actually an integral on this circle of FG bar. But that's not going to come into it now. All right, so the reason I'm changing perspective, so for those of you who are just thinking H2 is just a sort of a reconsideration of L2, it's just considering L2, but now as a Hilbert space of analytic functions. So I'm going to define the Cesaro operator on H2. All right, so H2 is a set of analytic functions. So if I choose an F from H2, right, I can define this integral and it'll give me an analytic function of Z. I can safely do all that. It'll have a 0 at the origin and then I divide it out. All right, so if you are good with a power series, you use the Cauchy product of a power series and geometric series, you can actually write out the power series expansion of this integral. And notice what you're getting here. The power series coefficients are the Cesaro mean. So there's the averages of the first n terms. Right, so essentially the Cesaro operator is the Cesaro matrix, right? The coefficients here are just going to be the columns, the nth column of the Cesaro matrix here. All right, so this means if the matrix representation of the Cesaro operator on H2 with respect to sort of the standard orthonormal basis Z to the power n is the Cesaro matrix. All right, so why am I making a big deal out of this? And you know, the Cesaro matrix is easy to understand, and now making it seemingly more complicated by defining an integral operator is because I need to discuss the eigenvectors of the adjoint of it. So it's nice to have a nice formula for the adjoint, right? So the adjoint turns out to be this integral operator. And the way you prove this is, again, you write out the power series coefficients of this thing. So F is an analytic function, so you can define this antiderivative and you work it out. And then you compare it to the coefficients in the adjoint of the Cesaro matrix, which is just going to be the flip of what we had before. So it'll be the terrace matrix where the terraces are going the other way. And then because it's just anti-differentiation, we can consider this analytic function. So W is a parameter in the open unit disk. And this is an analytic function on the disk. It's a function of Z. All right, there's a logarithm involved, so let's just be clear. Let's arrange things so that the branch of the logarithm you're going to choose is so that the log of 1 is equal to 0. So let's kind of make that unambiguous. So this is a nice analytic function. And you can actually show that using power series and stuff you learn in Calc 2, that this is an H2 function. It has square summable power series coefficients. And then using this handy dandy integration formula, right, you can show that these functions, phi sub w, are actually eigenvalues, eigenvectors with the eigenvalue w for I minus c star. So that's a nice little gem for. Now, there are other things I can say about the Cesaro operator, but I kind of want to focus on the problem of Halmos, so I will not discuss anything more than just these couple basic facts. All right, so here's the Halmos problem. He posed it at a conference. I forgot to look up where, but the question is, does the Cesaro operator on H2 or the Cesaro matrix on little l2 have a square root? So in other words, is there a bounded operator on H2 whose square is the Cesaro operator? So in terms of composition of linear transformations. So I've been getting into, as you will see at the end of the talk, I'll give you a little survey. I've been getting into square roots of operators these days. So I'm trying my hand at the Cesaro operator. All right, so the answer to the Halmos problem is yes. So I did not discover this. This is a known fact. And the approach to show it has a square root, the Cesaro operator turns out to be subnormal. I'm going to talk about more of this in a moment. And this is a result of Kriete and Trutt, and I'm going to give you kind of a survey of how that works and how I'm going to use it. And the spectrum of the Cesaro operator, we saw a piece of that. I computed the eigenvalues of the adjoint, and that goes a long way to proving that the spectrum of the Cesaro operator is the unit disk shifted over by 1. So the interior of the spectrum lies in the right half plane. And there is a H infinity functional calculus for subnormal operators. There's a 1976 paper of Conway and Olin, which says that you can, if you have an operator whose spectrum, the interior of the spectrum, if you have a analytic function, a bounded analytic function on the interior of the spectrum of a subnormal operator, I think I'm saying this right, you can actually take phi of that operator and get a meaningful thing. Okay, so the square root is going to exist. All right, but are these, except for minus c, are these the only square roots of the Cesaro operator? And I teach at an undergraduate college, so we're into formulas for things. So is there a nice formula for the square root I can put in a box, right, that a student could put on a flashcard or something like that? So that's going to be the focus of the talk. So all right. All right, so the approach that we did, so this is joint work with Javad Mashreghi from Laval University in Canada and Marek Ptak at the School of Agriculture in Krakow, Poland. Our approach here is going to be a matrix factorization of Hausdorff. So just look at this factorization. So notice there's a diagonal matrix with the reciprocals of the integers. I'm going to call that matrix D. And then notice there are these matrices W on either side of D. These are rather curious matrices. Notice that the rows of the matrix W are the alternating binomial coefficients, right? So I have 1, 1, 1. The binomial coefficients are 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, but I'm making them alternate in sign. All right, now, first of all, for those of you who are thinking, well, are you sure you can do this? I can, because every matrix involved here is lower triangular. So I'm going to have no issues with multiplying these matrices. Any entry I get by the usual row column operation is going to be a finite sum. So there's going to be no issues with multiplying this out. So Hausdorff showed this, and what's interesting is that the square of W is equal to the identity operator. All right, and I just want to emphasize here, there's no operator theory involved in any of this. It's just matrix multiplication. All right, so now you can almost see how to compute a square root of the Cesaro matrix. And matter of fact, you can see how to compute a lot of the square roots of the Cesaro matrix. Notice if I take the square roots of everything down the main diagonal, right? And then I square this sum, the interior W's are going to go away. The square of a diagonal matrix is just going to be the squares of the entries. So yes, I can get a square root of the Cesaro matrix using this Hausdorff factorization. So anyway, all right, but there's still a lot of work to be done. First of all, there's this beautiful theorem of Hubert and Leggett, which says if I have any infinite lower triangular, I can't emphasize this enough, lower triangular matrix A, then the following are equivalent. A is the square root. A is a square root of the Cesaro matrix. And then A is actually equal to these factorizations that I talked about for, right? So I can put plus or minus signs down this main diagonal, and it will give you a square root of the Cesaro operator, because the W squared is equal to I, and I'm just essentially going to be squaring this diagonal matrix, which is going to give me 1, 1/2, 1/3, and I'll get the Cesaro operator. So I'm using a little bit of notation here. A sigma is going to be this thing where the plus or minuses are down here, and the sigma is going to indicate what I have, minus, plus, minus, plus, plus, minus, you know, whatever choice of signs I'm going to have there. Okay, so this gives me all the lower triangular square roots of the Cesaro matrix, right? And I hope I'm saying matrix enough times. All right, matter of fact, they can actually, with some work, they can actually have a closed form expression for the square roots of the Cesaro matrix. That's a little bit complicated. So this is lower triangular because notice when I is less than j, these are the terms in the upper piece of the matrix. And here's a, you know, you sit down and grind that out. And that's what you get as the closed form expression for the lower triangular square roots of the Cesaro matrix. Okay. And by the way, I can make these slides available to anybody if you're taking notes and maybe I'm speeding through this kind of too fast. Okay, so that's this result of Hubert and Leggett. Now, there's a little bit of an issue, is that not all these square roots define bounded operators on little L2. Right? So yeah, I have a lot of square roots of the Cesaro matrix, but which ones define bounded operators on little L2? So that's the issue. Now let me give you an example to sort of make this clear that there is an issue. All right, suppose I were to make my choice of signs to be -1 here, and then pluses all the way down. So I'm allowed to make any choice of sign to give me a square root of the Cesaro matrix, but I choose to have this sign, a -1 here, and then everywhere down. If you do a little work in adding and subtracting, what you get is some infinite matrix B, which will turn out to be a bounded operator on little L2. Okay. And then -2 times this matrix. Well, the second summand is definitely not a bounded operator on L2. It doesn't even take L2 to itself, right? It takes the vector 1, 0, 0, 0, 0, 0 to the vector 1, 1, 1, 1, 1, which is not in L2. So this, although it's a square root of the Cesaro matrix, it does not define a bounded operator on little L2. Okay, so, all right, so now I have to figure out what choice of signs are going to give me bounded operators on little L2. All right, so I'm going to take a little tour into the construction of Kriete and Trutt. That is the technique that we use to clarify which of the Hubert and Leggett matrices give you bounded square roots. So recall these eigenvectors. So these are H2 functions, and they're eigenvectors for I minus C star, right? So here's an eigenvector, and it has an eigenvalue W. And what's going to be important here is that these, the closed linear span of these is actually going to be all of H2. All right, actually, this is not too bad to see. I think if you let W be 1 over N, I think if you let W be 1 over N, then phi of 1 over N is going to be 1 minus Z to the power N, I think, right? So essentially, this set is going to contain all the polynomials. And then once you contain all the polynomials and you close that up, you get H2. All right. Yes, David, I'm drinking from a New York Yankee cup. So here's a space of functions that Kriete and Trutt used. So for a function in an H2, take one of the eigenvectors for the adjoint of the Cesaro operator and take its inner product with F in the H2 inner product. Now that defines a function of Z on the disk. And it actually defines an analytic function of Z on the disk. Now I know it doesn't look like it because I have a big fat bar on the Z, but the inner product is in the second slot, right? So if you write out the inner products, that Z bar will go away. So this will be an analytic function on the open unit disk. And Kriete and Trutt made this a Hilbert space, right, by defining the norm. It's called a range norm, I think. So the norm of one of these analytic functions, capital F, in H is going to be defined to be the H2 norm of the function F that gives rise to this function, capital F. All right, now you have every right to be concerned that this is not actually a norm, right? Because one of the first things you have to have for a norm is that if the norm of a vector is 0, the vector had better be 0, right? So if this norm turns out to be 0, right? Or if the vector turns out to be 0, it going to have a 0 norm. And this is where if F annihilates all of these functions have dense linear span. So that'll help say that this is a well-defined norm and things like that. Okay, and it also ensures that this sort of the obvious map U which takes an H2 function and gives you this mysterious function f. It actually is a unitary operator from H2 to this mysterious space H. All right, now I'd like to do at least one computation, right? So if I were there, I'd have a blackboard and I'd be able to, every seminar talk, you should work out one detail here. So let me do this one, is that this, operator U, this unitary operator, intertwines the Cesaro operator with multiplication by 1 minus z. And what does this say? At least to me, the Cesaro operator is kind of difficult to understand, but a multiplication operator, at least by a very particularly easy function, is very easy to understand. But I guess the trade-off you have is that the Hilbert space at which this very simple operator acts on is actually a complicated space, but that's a tale for a different day. All right, so let's actually prove this. So let's suppose f is in H2 and it's given by u star f. Let's look at u I minus c times u star, right? And I want to show that's z times capital F. Okay, so here we go. So this is a function of z, and it's equal to u I minus c. U star is going to be f of z. Now, I minus c, f is going to be a function in H2, let u operate on it, right? And it's by definition, it's the inner product of I minus c f against the one of the eigenvectors for the adjoint of the Cesaro operator. Now bring the adjoint to the other side, right? And now use the eigenvalue eigenvector relationship here. So this is going to throw off a eigenvalue z bar. Now keep in mind the inner product is not in z bar, it's in some dummy variable which I'm not giving you. So we teach our linear algebra students that the z comes out in the second slot, right? And then what you're looking at here is just u, right? So that's u of z, and that's exactly f. So there you have it. So that shows that this u intertwines the Cesaro operator with multiplication by 1 minus z. All right, so I'm going to be making use of this identity. All right, so for some, okay, let's go back to the Halmos problem, which again was what operators are the bounded square roots of the Cesaro operator now. All right, so let's begin to assemble some of the pieces of all this. So if I have a bounded operator on H2, that's a square root of the Cesaro operator. A 2-second exercise here is going to say that A is actually going to commute with the Cesaro operator. So this is what this little prime thing means, that AC is CA, and you can almost see how that works. All right, so taking conjugating by U, you see that U star is going to be in the commutant of multiplication by Z on this sort of mysterious Kriete and Trutt space, H. All right, now it's sort of a standard fact, right? I'm having a little, it's sort of a standard fact that anything in the commutant, if the polynomials are dense and it's a reproducing kernel Hilbert space, then the commutant of multiplication by Z are the multipliers of the space. So U star is going to be multiplication by some phi, some analytic function phi, which is going to multiply H into itself, right? Okay, so Kriete and Trutt also quotes some other result. I can't think of it now, that I think the multipliers are actually H infinity, but we don't need to get that complicated to do what we're doing here. So U star is multiplication by 1 minus Z, right? A is the A squared is equal to C, so it has to be the case that phi is plus or minus the square root of 1 minus z. There are no other choices for it. Right, so phi is the function, the square root of 1 minus z, or phi is minus the square root of 1 minus z. However, all I've shown so far is that that's what phi has to be. That's what phi has to be. What I need to verify is that the square root of 1 minus z multiplies h into itself. Right, that's a detail that I need to check. Did I skip a slide? Ah, I did, right? I'm having a little problems here. The thing that makes what I'm definitely going to use here that makes everything work is that this mysterious space H is actually what's known as a P2 mu space. So I can actually re-norm the space H as an L2 space. I can slap an L2 norm on this thing. So there's a positive finite Borel measure on the closure of the disk, so that at least on the polynomials, the H norm is actually an L2 norm. Okay, so this, but by the way, will show the subnormality of the Cesaro operator, because multiplication by 1 minus z on P2 mu has an obvious normal extension, multiplication by 1 minus z on L2 of mu, right? So multiplication by 1 minus z is going to be subnormal, and if you're unitarily equivalent to a subnormal operator, which in this case the Cesaro operator is, then you're a subnormal operator. So that's how Kriete and Trutt showed that the Cesaro operator is subnormal. Right, so my clicker is all right. All right, so now we have the square root of 1 minus z. Does that multiply h to itself? And it does, because the square root of 1 minus z, if you write out the power series, the Taylor coefficients are actually absolutely summable. So if you want to use fancy language here, the square root of 1 minus z is in the Wiener algebra. So now you can fashion a proof so that if you have any function in P2 of mu, the closure of the polynomials in L2, there's enough uniform convergence going on that says you can, the square root of 1 minus z times something in P2 mu will again be a function in P2 of mu. Okay. All right, so let's put this all together. And this is a first thought on what the square roots, the bounded square roots of the Cesaro operator are. So again, this is joint work with Javad Mashreghi from Laval and Marek Ptak from Krakow. So a bounded operator on H2 is a square root of the Cesaro operator if and only if A is equal to plus or minus that infinite series, where if you're wondering where these numbers 1/2, 1/8, 1/16 come from, they are the power series coefficients of the square root of 1 minus z. Now this series converges in operator norm. Notice that I minus c, we talked about that the norm of that is 1. And this series converges, has absolutely summable power series coefficient. So this converges in operator norm. So how did I get that formula? Well, A is going to be, right, the square root of the Cesaro operator is going to be unitarily equivalent to multiplication by the square root of 1 minus z. And I write out multiplication as the square root of 1 minus z as multiplication by 1 minus multiplication by z over 2 minus multiplication by z squared over 2, and so on, right? And then I use the fact that each one of those multiplication operators is going to be unitarily equivalent to I minus C squared, and so on. Okay, so there are two bounded square roots of the Cesaro operator. And here they are. But you have every right to be a little bit disappointed so far, because I advertised, so I've shown that there are two, or we've shown that there are two bounded square roots of the Cesaro operator. Now you actually want a closed form expression for them, and that's what's going to come up next. All right. All right, so here's the final piece of the puzzle. All right. So notice that, do you remember we had these Hubert and Legert formulas for the lower, what is going on here? I'm skipping. It's causing me to skip too much. All right, so notice that a key observation here is that the elements of this series are all lower triangular matrices. Okay, so these are actually lower triangular square roots of the Cesaro operator. Right, so now I'm in good shape, because now I just have to figure out the signs. Right. Right, so now I just have to, so do you remember A sigma was this formula here, and I just need to figure out the signs. Well, the sign, if you look at the diagonal, the sign is determined on the diagonal, right? So this is a positive number, so if I want to know what the sign, the choice of sign is, I look at the diagonal entries of these A sigmas. All right, so if A squared is equal to C, then because A is equal to this lower triangular matrix, it's going to be an A sigma for some sigma, right? But it turns out the diagonal entries of each one of these matrices, because it's lower triangular, is actually pretty easy to figure out. And then again, I teach Calc 2 a lot, so I'm kind of an expert on summing series. So it turns out that you only have two choices. It's either ones or the minus ones. So when I created that unbounded square root of the Cesaro matrix, it was pretty easy to do. I just had to choose the first entry to be -1 and all the others to be positive. So the long and short of it is there are only two bounded square roots of the Cesaro operator, and here they are. It's the choice of ones or -1. So those are the square roots of the Cesaro operator. So I'd like to spend the rest of my talk giving you a survey of some other things that I found interesting about square roots of operators. So other square root results, some of these will be mine, and most of them will be by Paul Halmos. All right, it turns out that the zero operator is an interesting operator. Right, so the zero operator certainly has a lot of square roots. Any nilpotent operator of order 2 will be a square root of the zero operator. Amazingly enough, a result in Paul Halmos's what is it, Hilbert space problem book. This is a strongly dense set. He uses this as an exercise to demonstrate that the multiplication of two operators is continuous in the norm, but it's not continuous in other topologies in this SOT. All right, so I find the zero operator interesting. The unilateral shift, right? So most people look at this as just multiplication by Z on a classical Hardy space, so that's the matrix representation of it. If you like to think of this on L2, it takes a sequence, it shifts it over by 1 and puts a 0 in the first slot. All right, so does the unilateral shift have square roots? And the answer is no, right? So just about no shift operator has on any reasonable Hilbert space of analytic functions has a square root. When I did this Halmos problem, I didn't use his proof. I was trying not to use his hint, so I came up with a complex analysis proof. It's nothing ingenious. It's probably a standard fare here. So there's no square root of the shift. All right, so suppose that there was a bounded operator whose square is the shift, then it sort of the usual trick, any square root commutes with the operator. And then as I mentioned before, if you commute with any shift on some reasonable space, it's going to be multiplication by some phi in the multiplier algebra, right? And then you can kind of see this is heading for a gigantic crash. So the shift is multiplication by z. It's the square of a, which means it's the square of multiplication by phi, which means it's multiplication by phi squared. So the long and short of it is I'll have an analytic function on the disk whose square is z. And that's just no. All right, so it has no square root. So the Dirichlet shift, the Bergman shift, whatever, those don't have square roots.
Bill, can I ask a question?
Yeah.
I was stunned earlier when you were showing square roots that were matrices but not operators.
Right.
And I'm just wondering if it, like a question like this, whether there could be a matrix whose square is the unilateral shift or something like that, or are these results strong enough
I knew you'd
to
ask that, and I was messing around with this yesterday, and I don't know, but that's a good question, right? So so David makes an excellent point that I'm only talking about the bounded operators that define square roots. So David asks a good question: is there maybe a matrix which is an unbounded operator whose square is the shift? I'm going to guess the answer is no, because I think there's a linear algebra proof why. I think if you look at Halmos's hint, right, he looks at kernels and ranges of things. I'm going to guess no, because I think his proof doesn't really use bounded operators. But anyway. All right, what about the square of the shift? So does the square of the shift have a square root? That seems like a ridiculous question. Well, duh, it does, right? It's S, right? So the square of the shift, it has this matrix representation, right? And you can think of this as just multiplication by z squared on H2. So the shift, by the way, has ones along this diagonal. So the square is going to be this. It's kind of like a Jordan block. It just keeps on going down. So on a project I worked with Javad and Mark is, can I actually describe all the square roots of the square of the shift? And it turns out it's an interesting class of bounded operators. So just to make this easier to state here, just by separating the Hardy space into its even part of the power series and the odd part of the power series, you can show that S squared is unitarily equivalent to S plus S on H2 direct sum H2. So it's you have these sort of blocks here, and now you can write it as a matrix. So for a bounded operator on H2 plus H2, it's a square root of S plus S, if and only if it's of this form, right? So there's a 2x2 constant unitary matrix U, bounded analytic functions A, B, and C, which satisfy this functional equation so that A takes this form. So what does this mean? You take a pair FG, you multiply it by a unitary matrix, you get a sort of a perturbed version of F and G, you multiply it by these things. So now you're multiplying these pairs by linear combinations of functions, and then you multiply it by the adjoint. So those will be all of the square roots. And if you're thinking, well, how are you going to find functions that satisfy this? It turns out if you're good at outer functions, which Javad is, then you can actually find plenty of functions A, B, and C that bounded analytic functions that satisfy this identity. Now, by the way, I teach linear algebra a lot. So I like matrices. So I took some choices of U and of A, B, and C, and I worked out some interesting square roots of the square of the shift. So here's one. So you can check this out if you square this matrix, right? So this will be a bounded operator on little L2. If you square this matrix, you will get the square of the shift, right? And another judicious choice of U and functions A, B, and C, you don't even have to get complicated, creates this sort of cool looking square root of the square of the shift. Oh, I think these are cool looking objects. All right, let me do two more, the Volterra operator. So this is sort of one of the first operators to be studied, right? It's sort of what calculus students know is anti-differentiation. Goes from L2 to itself. Does it have a square root? Well, so Marek and Javad and I actually worked out that it does, and we classified them all. And then, unfortunately, we wish we read some papers beforehand. So Don Saracen and Rajavi and Rosenthal actually characterized the square roots of the Volterra operator. And they're these things, they're these integral operators. If you're wondering where the 1 over the square root of pi is coming from, it's coming from Laplace transforms. So the Volterra operator is actually a convolution operator in kind of an obvious way, a convolution with f with the identity with the 1, right? And so if you use a little fact that the Laplace transform takes a convolution to a product of Laplace transform, at some point you're going to need to compute the inverse Laplace transform of 1 over the square root of s, right? And that's where the 1 over pi comes from in this rather weird square root. Anyway, I used to teach engineering, so I got very good at Laplace transforms. So finally, I teach at a small college, and we all have to pitch in various things that are a little bit outside our comfort zone. So I have this year, I have a student writing in the physics department, writing her honors thesis with me, and she has chosen the Fourier-Plancherel transform. So the Fourier-Plancherel transform is this integral where you have to understand it as a limit in the mean. All right, and let's see, if you use Hermite functions from physics, they're an orthonormal basis for L2, and they actually diagonalize the Fourier transform. All right, so notice you have this sort of little mini diagonal matrix here that repeats itself infinitely often. So it seems you're getting the tensor of D with the identity operator. And let's see, oh God, I forget the name of this theorem. Tomitia's theorem or something about tensor products of operator algebras. So the commutant of the Fourier transform you can kind of write as a tensor product, and then you can write the square roots of the Fourier transform as the diagonal, as the M tensor A, where M is a diagonal 4x4 diagonal matrix whose square is D, and the A is any bounded idempotent. All right, so what is her project on? Is certainly not tensor products, although she's going to have to understand it. There's actually a beautiful formula of Mailer from 1866. And you have to understand it as a limit in the mean, which actually gives you an integral form of the square root of the Fourier transform. So what Brianna is going to do is she's going to look at these sort of things and make interesting choices of A's and M's that maybe she can write out different versions of Mailer's formula. And hopefully the physics department will think that's sufficient enough for a honors thesis in physics. And then she's going to go and work in a lab somewhere. So anyway, thank you so much for listening. And I really do appreciate being given the opportunity to talk about something that I think is kind of cool. So there we have it.
Hey, sorry, someone just entered my office right now at the moment you're finishing. Thank you very much for your talk, Bill. Okay, the person left. Sorry, I think it was someone from the clinic, some clinic person. Okay, thanks for your talk. Do you have any questions?
Bill, what about S cubed?
S cubed does not have a square root. If you look at now, Mark Ptak is very much into tensors and all this other stuff. So he is drawing me into what about the infinite, what is it, dilation of S, so S infinity, infinite copies of that, and can you characterize all those square roots? So you can actually write down the square roots of S to the fourth, and but S to the odd power, they don't have square roots. But you want to know, does it have cube roots, and do they come an interesting class of cube roots? I'm going to imagine so, but.
A question, Bill?
Yeah.
So this theorem, is it by Hupert?
Yeah.
So, okay, so that says that among these matricial square roots, there is, and most of them are unbounded as operators. So all other matricial solutions are eliminated. I mean, that's part of their theorem?
No. I hope I stated it clearly. It says if you have a lower triangular matrix, it's a square root of the Cesaro matrix, if and only if, blah, blah, blah. There are actually square roots of the Cesaro matrix that are not triangular.
Oh, okay, I'm sorry. So if you impose lower triangularity, then that's all of them. There's nothing else.
Right.
Is showing that there's nothing else, is that hard?
I think it is. It definitely takes a lot of computing and calculating. For example, if you have any lower triangular matrix, just, you know, a 5x5 matrix that's lower triangular, and I think at least one of the diagonal entries can't be, no, at most one of the diagonal entries can be 0. There's actually an iterative procedure to actually get what the a square root is. So you actually have to work through that detail. There's an infinite version of it. So they're a little vague on the proof. So I kind of worked it out enough myself to know that it's a rather unpleasant computation. So.
Hi, Dave.
What?
Dave Trutt. Hey.
Hey, is that David Trutt?
I think you're mute. Your audio is muted, Dave.
Dave, where are you at the moment?
You're still muted.
Maybe we'll stop the recording.
Oh, here it is.